Hello students, welcome to today's lecture of Theory of Machines. In today's lecture, we will discuss the classification of cams. In the previous lecture, we started the topic cam and follower. We discussed what is cam and follower mechanism and why it is required and what are its utilities. We also defined the cam and further discussed the advantages of cam and follower mechanisms. In today's lecture, we will discuss the classification of the cam. So let's start with the classification of cam. The versatility and flexibility in the design of cam systems are among their more attractive features. Yet, this also leads to a wide variety of shapes and forms and the need for terminology to distinguish them. Cams are classified according to their basic shapes. Cams are classified as follows, depending on the type of input movement. That is, if the input link, that is the cam, rotates, that is, has an angular motion, then we call it as a disc cam or radial cam or a plate cam. And if the cam movement is translational or linear, that is linear oscillation, that is linear to and fro motion, then we call it as a wedge cam or flat cam. Then we have cylindrical cam or barrel cam, depending on the shape of the cam. If it is cylindrical and the groove is cut on the periphery of the cylinder, then it is a cylindrical cam. Then you have conjugate cam. In this, two disc cam are connected together. Next we have globoidal cam, depending on the shape of the cam again, whether it is concave or convex, they are classified as globoidal cam. Next we have spiral cam, depending on the shape of the groove cut. In this case, the shape of the groove that is cut on the disc is of spiral shape. Further we have spherical cam. Again, the shape of the cam is spherical and the groove is cut over the periphery of the sphere. And at last we have end cam. Now before we get into the further discussion of classification of cam and follower, let us discuss one important point in the cam and follower mechanism. For that, let us see this cam and follower mechanism. This is a cam and this is a follower. Here also, this is the cam and this is the follower. What is to be noted is that as the cam rotates or translates, the cam can drive the follower only in the upward direction as shown here. Whereas when the follower tries to come down, there is no tensile force that can be applied by the cam onto the roller. So it comes down due to gravity in this case. To ensure that the contact is always maintained during the upward motion and the downward motion of the follower, normally we use springs as shown here. The spring is connected between the guide and the follower such that when the cam is rotated and the follower goes up, the spring is compressed as shown. So when the cam shape is such that the follower wants to come down, it is this spring which will try to return it back, ensuring that the contact between the cam and the roller is never lost. In the absence of the spring, we see if we leave it only to the gravity, the maximum acceleration can be g in the downward direction. But if you want the follower to have higher acceleration than g, that is acceleration due to gravity, then there will be loss of contact. That is, the cam will rotate but the follower will not follow the cam profile. So to ensure the contact during the entire stroke of motion, we use this spring. Similarly, for this oscillating roller follower, again we have spring to ensure that the follower can be driven in this direction by rotation of the cam, but to ensure that the contact is always maintained even while the follower has to come in this direction, it is the spring which will help to maintain the contact between the roller and the cam surface. There are other ways of ensuring this contact during the entire duration of the cam without using spring. This is as shown here. In this case, a groove is cut in the periphery of a cylinder and the roller of the follower is placed inside the groove, which is always intact. So whatever may be the acceleration of the cam, the contact between the cam and the roller of the follower is never lost. So having learned this, let's move towards the classification of the cam. So let's see the radial cam or disc cam. This is a typical disc cam, which is having the rotational motion. A cam in which the follower moves radially from the center of rotation of the cam is known as a radial or disc cam. Radial cams are very popular due to their simplicity and compactness. As you can see here, cam is mounted on this fixed link, that is the foundation. This is the link 1. So cam is link 2. So there is a revolute pair between 1 and 2. And this is the output pair, which is a follower. And as we see, as the cam rotates, depending on the profile or shape of the cam, the follower will have the translatory motion along the prismatic pair between the link 1 and the follower. So this is a 4-link mechanism. The fixed link 1, the cam is link 2, this roller is link 3, and this roller is having revolute pair with this output member or the follower, which is the link 4. So the uniform rotary motion of the cam will have rectilinear oscillation of the follower along the guide, which is a prismatic pair. This is the prismatic pair. This cam and follower mechanism can also be compared with the slider cam mechanism that we studied earlier as shown here. So moving ahead, next we have wedge cam or flat cam. This is a typical wedge cam. So there is a cam which is having a wedge shape. Depending on the profile of the cam, as this is wedge shape, cam oscillates in the horizontal direction and the follower will move along the vertical direction along this prismatic pair between the follower and the guide. This is again a different type of wedge cam in which the wedge is having a definite profile and it is having a translatory motion which imparts follower the vertical motion as shown. Here we again have a 4-link mechanism. This is the fixed link. This is the cam, which is the link 2. This is the roller, which is the link 3. And the follower is the link 4. Depending upon the profile of the cam, as this wedge shaped cam oscillates in the horizontal direction and the follower will move in the vertical direction along the prismatic pair between the follower and the guides. Roller is 3 and the follower is link 4. Next we have cylindrical cam or barrel cam. So this is a typical cylindrical cam or a barrel cam. In a cylindrical cam, a cylinder which has a circumferential contour in the surface rotates about its axis. The follower can have either the translatory motion in this case, or in this case it is having the oscillating motion. Cylindrical cams are also known as barrel cams. As you can see, the profile or the contour is cut along the periphery of the cylinder or the barrel, and according to the profile on the cam, the follower will have its motion. In this case, translatory motion. So these are the examples of barrel cam. Next we have conjugate cam. A conjugate cam is a double disc cam, the two discs being keyed together and are in constant touch with the two rollers of the follower, or in this case the flat follower. So these are the two discs which are keyed together, and in this case the follower has a positive constraint. Such type of cam is preferred when the requirements are low wear, low noise, better control of the follower, high speed, high dynamic loads, etc. So this is the conjugate cam. Moving ahead, next we have Globoidal Can. This is a variation of cylindrical cam. In this case also, the contour is cut over the surface of the cam. A globoidal cam can have two types of surfaces, convex and concave. A circumferential contour is cut on the surface of the rotation of the cam to impart the motion of the follower, which has an oscillatory motion. So this is a convex surface on which a contour is cut and the follower is having the oscillating motion. Similarly, this is the concave cam in which the contour is cut and again the follower is having an oscillating motion. The application of such cam is limited to moderate speeds and where the angle of oscillation of the follower is large. Next we have spiral cam. This is a spiral cam, a multi-level spiral cam. A spiral cam is a phase cam in which the groove is cut in the form of a spiral as shown here. The spiral groove consists of teeth which mesh with pin gear follower. The velocity of the follower is proportional to the radial distance of the groove from the axis of the cam. The use of such a cam is limited as the cam has to reverse the direction to reset the position of the follower. It finds its use in computers. Moving ahead, we have spherical cam. In a spherical cam, the follower oscillates about an axis perpendicular to the axis of rotation of the cam. Note that in a disc cam, the follower oscillates about an axis parallel to the axis of the rotation of the cam. A spherical cam is in the form of a spherical surface which transmits motion to the follower as shown here. Next we have end cam. This is a typical end cam with a roller follower. In an end cam, the end of the cylinder is the working surface and the follower translates along or parallel to the axis of rotation of the cam. So this is the classification of the cam. We have various cams depending on the types of motion, type of shape, and also according to the follower motion, each of which have specific applications. So this is all about today's lecture. I hope you have understood the various types of cams. In the next lecture, we will see the classification of the follower. Thank you.